So that's kind of the simple approach. The more complex approach then is to use some kind of vision-based tracking. We already talked about this in lecture 5 for a bit. So again, the goal is that the primary goal is we want this 6 degrees of freedom pose of our mobile device with relation to the environment. And when we're already using vision, then we can also, as a secondary goal, actually create a map of the environment. So I already mentioned SLAM is a common way of doing this. In the mobile AR context, you also can have extra special hardware for this, usually a depth camera. For a time there was Project Tango from Google, which is a tablet with directly integrated depth camera, or you can buy add-on depth cameras from various smaller manufacturers that provide additional information. But if you want to reach a larger audience with normal devices, so to say, then you need to kind of rely on just having a single color camera available. And then you can either choose the marker-based approach or SLAM, which I'll be going into a bit more detail in a moment. So first, let's talk about the dedicated devices, which aren't that common. Just a brief detour, basically. The fundamental idea behind a depth camera is that for each pixel, you don't just get color values, but you also get distance values. One approach is to just use stereo cameras, so you have two separate color cameras with a bit of distance in between. This is kind of a replica of how the human vision also primarily estimates depth. So the parallax between these two slightly different viewpoints can be used to basically triangulate the distance to each pixel. Problem is, for this to work, you need to find so-called stereo correspondences between the two images. So you need to figure out which pixel in the left image, for example, belongs to which pixel in the right image. And if you're looking at something like a featureless white wall, then that might be a bit difficult. Many computer vision algorithms actually fail at that. Or if you have a very repetitive pattern that you're looking at, then this sort of algorithm often gets confused. On the other hand, what this Tango device, for example, had built in is a so-called dedicated depth camera, which either has actually a time of flight sensor that measures the time light takes until it's reflected back from the environment and arrives again at the sensor, or it has a structured light camera that kind of projects an additional infrared pattern into the environment and then measures how much this pattern is shifted with respect to the emitter. So all of these are possible approaches for depth cameras. Once again, I don't want to go into too much detail on how depth cameras work. The important part is that for any mobile application with such a depth camera, you need extra hardware or dedicated hardware. So you either need to kind of bolt an extra camera to the back of your tablet, or you need to get a specialized tablet that actually has a depth camera already built in. And so this is only useful for very, very specialized applications. So as a really short detour, this was also quite a couple of years ago, a friend and I tried to compete in a challenge from Innocentive, which is a company that kind of gives out kind of invention challenges. Don't know how to describe that. And the challenge was, please measure the volume of a pig. So that was kind of a weird experience first, but then we had this idea of actually taking a Kinect depth camera and mounting it to the back of the tablet and using that to then kind of fit a cylinder through the pig and estimate how much that pig weighs. So that was the end goal, to estimate the weight of livestock, basically. If I remember correctly, our entry didn't get selected in the end, but it was actually like using a dedicated depth camera on a mobile device to create some augmented reality view of how much that specific pig might actually way, for example. But yeah, that was a dedicated device and definitely not something suitable for a mass market application. All right, so if you want people to be able to use their own mobile devices without extra hardware, then you usually need to fall back on some sort of tracking that only uses one single color camera. And the fundamental approach, or the easiest approach, which people have been using for also 20 years at the very least, often with AR Toolkit, for example, is to use these fiducials. So usually you have a big black border that can be easily identified by a computer vision algorithm, by a very simple one, and then you have that identifying pattern in the middle. And that, in combination with a bit of geometry, gives you the pose of that marker, and then you can put virtual content on top of the marker. These patterns don't look very appealing, so people are also using so-called image targets in many cases. Here the idea is that you have a predefined image, like for example this book page, and that the features on this image are known to the system in advance, and then it can detect these features in the camera image and use that to calculate the relative pose again. So this is kind of the most straightforward approach people are using for many commercial augmented reality applications. I think, for example, the IKEA catalog uses that. So you need an extra IKEA app, and then if you look into the catalog with that, then it will recognize specific pages in the catalog and display additional virtual content on top. So for the fiducials, it's rather straightforward to imagine how that works. So you need to find this big black area in the image, and then this white area in the center, and so on. For the image targets, it's slightly more involved. There's usually some kind of so-called feature descriptor used for that. A very commonly used one is SIFT, but there's also SURF and ORB and so on. So there's various types of feature descriptors. SIFT is just the most widely known one. This means scale invariant feature transform. And the fundamental idea here is that I take small distinct areas in the image, and create a numerical descriptor for them, which does not change if I modify the size or the orientation of this patch. And then I can have basically one training image, let's say this playing card here, and these purple arrows kind of indicate the various SIFT descriptors created for that playing card. And these basically I pre-calculate and store in my app, and then in the next step, in the camera image, I calculate also this bunch of SIFT descriptors across the whole image. And in the second step, I can then create a match between the predefined SIFT descriptors in my training image or in my image target and the camera image. And here you can see there's a few kind of spurious matches that don't actually fit the playing card, but 95% match the exact area in the camera image which I actually want to detect. And then from the geometric transformation for each individual descriptor, I can then calculate the overall transformation between the image target and the camera image and use that to put my virtual content on top. All right, so all of this kind of requires that the user has some sort of target already available in some sort of printed material, either a book or a printout or just this fiducial marker. A bit more advanced approach is SLAM. We already briefly talked about this in general. It means simultaneous localization and mapping, and was originally developed for mobile robots. So robots moving around in an unknown environment use this camera image to create a map and also locate themselves within that map as it's being created. This does require quite a bit of processing power, so you need a somewhat recent device for this, but for example, this ARCore framework from Google or ARKit from Apple, they both basically use this approach to create this environment map and location of your device at the same time. The basic idea here is, again, that I actually have these stereo correspondences for subsequent images. So if I move my device slightly, then the camera view will also move slightly. And then I can match points between these two images. And if I know by how much my device has moved approximately, then I can put that data together to create 3D points and collect them in a map over time. Usually you also need the IMU for this to work, because, for example, if you would not have the IMU and I move my device by 10 centimeters, then purely from the camera images, you could not decide if I moved it by 10 centimeters in front of a small area, or if I moved it by 20 centimeters while I was standing farther away. So the camera images would basically look exactly the same. And so, because the IMU is capable of measuring relative motion, this is one use case where that actually makes sense, because I only need to know the approximate distance between two subsequent images. So if I move it by 10 centimeters to the right, then this is something the IMU can measure without too much drift. And then I can use that information to actually build the environment map with an absolute magnitude. Without the IMU, I would not know any absolute distance in the environment. I would still be able to create this point cloud of my environment, 3D point cloud, but I wouldn't know any distances, any absolute distances. As I mentioned, ARKit and ARCore are frameworks that enable this on quite a number of recent smartphones, so even not so expensive ones offer that by now. You can check out what devices ARCore actually supports. So one thing here is, because for this SLAM algorithm to really work accurately, you need to know the offset between the camera and the IMU, kind of like we talked about previously with Daydream 2. And so only those devices which are, for example, certified by Google for use with ARCore actually have this information available. I think you can trick it into working on other devices too, but then it will be less accurate, because the information will be not known about what the actual offset between the IMU and the camera is, for example. In addition to that, you also need to know a bit of calibration about the camera. So you need, for example, to know the field of view and the focal length and so on. This is something you could measure on your own, but of course, if you want to reach many users, then you don't want them to first measure focal distance and so on of your camera. So this is also something that usually needs to be pre-calibrated for this to work. And one important feature both of these frameworks bring along is so-called plane detection. So they, as I already mentioned, they create a 3D point cloud of the environment, but this point cloud doesn't yet have any kind of semantic information. So you just have a number of 3D points that are objects around you. And this plane detection approach uses an algorithm called RANSAC usually to detect larger flat areas within that environment. And that actually is quite important for proper interaction with this virtual content, because you can then, for example, place something actually on the floor, and you can actually display a proper shadow for things. This is also something that helps surprisingly much with a realistic impression. So if you don't have a shadow, then these virtual things kind of appear to float, even if they're in the correct 3D location. Once you add a bit of a shadow, then it suddenly appears to be much more realistic. And of course, when you know planes in the environment, then you can also kind of have a point where you can project data from the touchscreen too. So when you kind of touch the floor, the view of the floor on your device, then you can, for example, place an object exactly on the virtual floor plane. And that again wouldn't really properly work unless you actually have this additional algorithm running in the background that detects planes in this 3D point cloud.